evening, everybody. My name is Andy Long, and I'm Pro Vice-Chancellor for the Faculty of Engineering. And occasionally I have the pleasure of introducing an inaugural lecture from one of our new professors. We have to take new as being a slightly elastic term, but new he is. Hervé Morvan is Professor of Applied Fluid Mechanics. He is Director of the Institute of Aerospace Technology and also Head of the Gas Turbines and Transmissions Research Centre, helpfully shortened to G2TRC. So I'll tell you a little bit about Hervé, and then he's going to give you a presentation. After the presentation, it is traditional that we don't ask the audience to offer questions, but I'm sure that Hervé will be pleased to talk to you about any of his equations and derivations afterwards, if you wish to speak to him. Hervé was born in July 1973 in Brittany in France, and winding forward some years, he studied at the Engineering Grande École in Paris, graduating with a commendation in 1996. And he also miraculously obtained an MSc with distinction from the University of Glasgow in the same year, although that's because he was on exchange, I think, for the last year. So managed to get 2 qualifications in that time. He then spent 2 years doing national service, most of that time spent in Morocco, and then came back to the UK to do a PhD at the University of Glasgow up until 2001 in computational fluid dynamics, which of course has been a major topic for him ever since then. He spent 2 years in industry working for AEA Technology, working on CFD software in Harwell and also in Paris. And then in 2003 he gained a lectureship at Nottingham, first in civil engineering and then transferring a bit down the corridor in 2006 to the Department of Mechanical Materials and Manufacturing Engineering. And soon after that he joined the Rolls-Royce Transmissions UTC. And again, you will see this has been a major focus of his work and I believe an inspiration to the work that he has done since then. In 2008 he was promoted to Associate Professor and also awarded a Royal Academy of Engineering Industrial Fellowship with Rolls-Royce, which meant that he spent some of his time working more closely with the company. In 2011 he was promoted to Reader and also appointed Head of Fluids and Deputy Director of the Rolls-Royce Transmissions UTC. And then in 2013 he was appointed Director of Research for the newly formed Institute for Aerospace Technology at the university, and then a year later was awarded a personal chair and was appointed Director of the Institute for Aerospace Technology. Last year Hervé formed the aforementioned research group G2TRC and established it within new facilities with investment from the National Aerospace Technology Institute alongside other companies, particularly Rolls-Royce. And then finally this year he has been awarded a fellowship at the Royal Aeronautical Society. Hervé tells me that he reconciles being Breton, French, European and living in the UK without difficulty. You should judge that for yourselves. He notes that he feels very French when it comes to food and rugby. So Hervé is going to give you his inaugural lecture, and I'm not going to either pronounce or translate the Latin. I will leave Hervé to do that as a more classically educated person than me. But the English title of his presentation will be Simulating Performance from the Pool to the Air.
Thank you, Andy. Hope the mic is on. I think it might be. Can you hear me? Yes? Okay, so, wow. I don't know where to start. It's one of those lectures where I'm actually more nervous than I probably would normally be, but I've got quite an audience. So thank you very much, everybody, for coming. I think giving the time of day and say a year, possibly. I'm really delighted by the turnout. I'm delighted that my parents also managed to come from France. And I must stress that I will make use of the Queen's language from time to time in order to assist them. I was delighted to see that some of my colleagues already started this in the hall or through email, having noticed that my parents were in copy of some of the emails. So Adam in particular told me that he spoke French like a Parisian, which I didn't quite know what to make of, but so far so good. Thank you as well for indulging me tonight, because it's really a pleasure to have the opportunity to talk about things I'm really interested in. That's a euphemism. Aerospace, and modeling, and I hope you find it interesting. And also because these days I don't get to teach much or lecture much, so I'm really keen to do that, and it's lovely to see the mix in the audience. I recognize the purple shirts, the PhD students from the IAT, and I think I can just about see some of our aerospace engineering students too, so welcome to all of them in the year when we launch basically this new course. I also wanted to thank the Faculty of Engineering, and in particular Diane Karim, who's done a fantastic job, because if you found the place and if everything is organized, that's greatly due to her. So we're on Twitter, and we're also being filmed, and this is why we are playing with so many microphones. The idea of this is that we might actually use the outcome of the filming to go on YouTube at some point and make the case for what it is we do at the University of Nottingham more broadly. There will be an exam question at the end. This is a lecture after all. Students always ask what it is they should know. It's very simple in this lecture. You just have to recognize every single aircraft, which picture will be on display. So for Richard it's going to be very easy. For others it might be more challenging. And of course success will determine which drink you might be entitled to at the end. And we've got some nice fizzy drink, as we call it in France, obviously, for you afterwards. So, now down to the title of the lecture. Who knows what this basically motto is? Yeah, it's the Modern Olympics motto. It was basically adopted by Baron Pierre de Coubertin at the launch of the Modern Olympics. And basically it reflects the values of, I would say, athletics in general, in terms of basically going further, higher, and stronger. Of course, this being an Olympic year in Brazil, but also due to an association I might have had in the past, so I will not display the outfit for you tonight. This basically also made sense, but it's also relevant for what we do in aerospace, because we are asking aero engines basically to operate basically at higher speeds, higher temperatures, higher pressure. So basically that constant challenge is perfectly described and encapsulated, I think, in this. And yes, I did 2 years of Latin in school. I wasn't very good at it. I then went on to do some more technical studies, and I think it has served me better. But I still remember a little bit of Latin. Okay, so Andy mentioned where I was from. I'm from the Celtic part of Brittany. We have a lot in common with basically, yes, Ireland, but also Cornwall. We are slightly different. We speak a Germanic language. So I'm from Brest in Brittany, which is this little blob here. Really a country boy, I would say, or seaside boy. And Brittany is, of course, very famous for its seafood. Beautiful old villages. This is a UNESCO site in Locronan. And of course we know a thing or two about sailing. We might have had some encounters with Britain in the past, and we've had some very famous privateers who have taken on basically the Royal Navy over the years. This is basically La Recouvrance. So Recouvrance is the name of the river that goes through my hometown of Brest. But it's also a ship that was reconstructed probably 17 years ago out of woods that they found in the river that had been left to soak. And in 1998, there was basically a tall ship event organized for the first time in Brittany, and the city decided to build that ship. So this is basically a coastal patrol ship. It's very, very fast. And this is basically also to signal that I'm here, but a lot of Britons are dispersed all over the world for historical reasons. I think we are the first diaspora in Paris, and if you go to the Montparnasse area, you will struggle, really struggle, not to find any Breton basically places. Brittany is also famous for other things. We might be slightly headstrong. I call this, I suspect determined, I know what I want. And this is very encapsulated in Obelix, if you know there. And The trait that I might take away from Obelix is that I don't need the potion to be fairly energized, and some of you have probably suffered from that. And as you can see, of course, we resisted the Romans. This is an historical fact for forever, from basically this little place in northern Brittany. The reason for putting this is that in my spare time, one of my real passion is comic books and illustrated novels. For my sins, I have crates and crates of these things. And I started very young with those. So, key question, what is this aircraft? Very, very early on, and you probably know that the French-Belgian, if you don't, you will now, school basically of graphic novels is one of the best there is. I like nothing more around Christmas period than absolutely doing nothing, sitting by the fire, having ordered from a well-known online distributor from their French, basically branch, 1 or 2 boxes, so you're talking 10 or 20 volumes, over to Britain, and then that's basically a light relief for me. Okay, so I'm from Brittany, as I said before. That's a picture from my childhood window. So if I looked on the outside, that's what it looks like. And that has been developed quite a lot, because when we built the house, well, there was no road, and for a long time we only had a gravel track to go to the house. But this is what it looks like as of last summer. And unlike Ireland, it is sunny in Brittany most of the time, including in summer. And I spent a lot of time really dreaming about what I wanted to do and studying mathematics here, because as you probably know, the French system is quite meritocratic, and if you want to join the Grand École scheme, you have to go through a fairly, maybe challenging is the right word, basically mathematical entrance exam. So if our students who are in the room think they have it tough, we used to have a 4-hour examination in mathematics every other week, and every other week we had a 3 to 4 hour examination in physics. And every week I had one 1-hour oral exam in math and one 1-hour oral examination in physics. And you do that for 2 to 3 years, then you can start engineering. Okay? And if you so I spent a lot of time doing that there. And so when I moved to the UK, it was great to start to do CFD, because CFD was a mix of engineering with, of course, a lot of numerical analysis. And because I specialized in those first years in math, I didn't follow on with physics. Then, yeah, I looked at that window for many, many times. Okay, so I also spent a lot of time, I'm a bit of an aero geek, I'm afraid. So can you just name those aircraft, remember? That will determine your drink intake at the end of the evening. A film was made about this very famous event here. This is Sam Shepard. The aircraft is wrong. Bonus question, what was the real aircraft like? And if you can name the character in these 2 pictures, who is still flying, and who in, I think, 2008, actually had, I think it was an F-15 flight while he was well in his 80s, and that would be great. He's currently 93 and on Twitter. So if you want to know about basically this activity, this gentleman is General Chuck Yeager. Yes, sorry, I liked my aircraft, so I thought I would probably join the Air Force. I spent a lot of time trying to do this. I did sit in a Mirage not that long ago. The Air Force, the French Air Force indulged me on that one. I probably couldn't have done it because, boy, oh boy, the cockpit is tiny, very, very claustrophobic. But I did try to convince my dad when I was 16 to do an apprenticeship. And surprisingly, the French Air Force mechanics school had 3 basically options. One was power and propulsion. One was airframe, and the other one was basically a mixture of avionics and weaponry. And the one I wanted to do was aero engine, so it started quite early. In Brittany, education is a premium. It's really seen as something you ought to do. So my dad said, no, I won't sign you off. You can do better. So that was the end of it. Told you I'm from Brittany, so I thought for a minute that I'd made a mistake. Maybe I should have tried to say I want to join the Navy. If you can name these aircraft, that would be great. They were retired this summer. It's a very famous Dassault type of aircraft. Just retired, and this is the last flight of the type, basically in July over the coast of Brittany. But my dad also said no. So Later on, I did try ENAC after I did the math studies, but I discovered that I have an eyesight deficiency. And having passed the written exam, having passed the oral exams, I went to do the medicals, and they said, well, the danger is that if you join ENAC, you're a civil servant. We pay you to study, we pay to train you, and if your eyesight means that you can't basically do the job, we won't take the risk. So I went to Paris and then to Glasgow, and I think the rest is history. There were quite a few detours along the way, because after Glasgow I spent 2 years in an exotic place, as Adam would call it, doing my national service, came back to Glasgow for the PhD, down to Oxford or Harwell to work at AEA, and then Nottingham offered me the opportunity of a lectureship, and I've been in Nottingham for 13 years now, so it feels quite a long time. I would say 3 or 4 years were a little bit lost, because when I came, I didn't quite know the university system. Except for my PhD, I'd never been to a university, so it was really, really new, unlike the French regimented system. But once I found my way, I think that I managed to do a few interesting things. So in the early days, I arrived in civil engineering, and I had trained as what we call in French an hydraulicien, somebody who does hydraulics. It doesn't exist in the English dictionary, I found out. So I just put a picture, and I just put the French definition here. Basically, an hydraulicien is somebody who does fluid mechanics but applies it to basically hydraulic dams or nuclear stations. And this is basically where I started. I did quite a lot of work here. And initially, I also did some more fundamental work. And one of the striking things is that in hydraulics, there's a long heritage that is quite empirical, quite heuristic. Of course, people way back didn't have means to do any very sophisticated, basically calculations. And the geometries are usually a little bit more complicated than our manufactured or man-made geometries. So one of the first pieces of work I did was a collaboration with Professor Donald Knight at Birmingham, and we wrote a paper to try and bring together concepts on roughness between hydraulics and basically advanced fluid mechanics. And that won basically the 16th Schumacher Award from the International Association of Hydraulics Research in 2009. It's not a very practical paper, not at all, but I just wanted to stress to my colleagues who think that I only do some easy and applied stuff that I have done a little bit of more fundamental work before. The other thing I did, which was very interesting, was basically simple application. Remember I said that in hydraulics we worked on ducts and channels, and we tried to understand how fluids get mixed or heat is exchanged. And if you imagine that this is basically a rectangular channel with 2 side walls and a bottom wall, and the liquid is flowing down, basically, historically people have tried to understand how they might calculate basically the force distribution, the flow recirculation in some of those. And if you take a cross-section of the channel, you might be able to split the flow, so this is basically a volume of liquid, into regions such that the shear force on that wall is exactly balanced by basically the weight of fluid that is coming down. But of course, if you do that, oops, did I miss something? Yeah, if you do that, you're forgetting 2 terms, which are basically the term resulting from the shear on that division line, but also the shear force that might exist as a result of the flow recirculations into themselves. So guess what was the name of the game? Well, some very famous name, Rayleigh, Culligan, if you do any hydraulics. Schlichting, boundary layer theory, anybody has read Schlichting? Tried this problem, and so did Einstein, actually, the son of the very famous gentleman who was a professor of hydraulics at UCLA until the 70s. And the name of the game was, of course, hey, can we find the line CH, yeah, this line, such that these 2 terms are nil? Because if we do that, if it exists, then the guys who try to resolve this problem to have a simple balance between shear force and weight, well, we're right. So I did this for quite a while with one of my French students from École Centrale in France. I've had quite a few of those for some reasons. Nicolas de Cacqueret came here, and then I continued with Kamran Ansari. Yeah, if you want to read more about this, we have some papers on that. Interestingly, Nicolas now works from the Safran group, which shows that hydraulicians are probably decent modelers and aero-engineering specialists. He works on their rocket program, and he's now coming back onto the aero engine program, and I bump into him every year at the ASME, basically Turbo Expo conference, which is a big conference on aero engine. It's lovely to see him every time, especially because he's really done very well for himself. The other thing that might interest you, it's made some of my friends laugh a little bit, was that with one of the students I shared with, Nigel Wright, a former academic here, we were basically roped in working with geographers to look at a mega flood, a super flood in the Altai. Now, we're not talking any simple river flow here. A river flow is 100 to 150 cubic meter per second. This is basically a quaternary era dam break with 6 to 9 million cubic meter of water per second coming down. So they roped us in because they actually looked at the landscape in this part of the Altai region, and they could see sedimentary deposits at 400 or 500 meter high. Made no sense. How can you get sedimentary deposits at such elevation? And this is a paper, and we actually worked on this, so this is what my expert colleagues put together. So this is the supposed location of the dam break, and we used modeling to try and figure out how this thing might have broken. And then we did some simulations, and we tried to look at basically, so the squares, the squares are some data for basically some sedimentary deposits and some sandbars. And basically the crosses as a model to try and see, if we got the sequence right in order to understand how this thing might have happened. Detective work, we didn't make any money on the back of doing this, but it's quite an interesting activity. And this goes back, so this is part of my past, if you want, before I moved more fully into mechanical engineering. Then, of course, I think I've got 2 colleagues from ANSYS, I think, who are in the room, or 3. Maybe I think I've seen Chris Carey as well, so that would make it. Yeah, Chris is there, so that may make it at least 4. I had the opportunity to work on basically the Speedo program for the Olympics, leading to the London Olympics in 2008. That was quite fortuitous, really, because the gentleman who really developed this idea was Barry Bixler, an engineer from Honeywell, US. Who was a swim dad, as we call them, so he used to accompany his daughter. And because he was one of those engineers who couldn't let things rest, he actually built a model of hands to understand the effect of the hand through swimming. And basically started to propose this to Speedo in order to support their design. And he supported the 2004 Olympic event, the FS2 suit, if you're following this sort of development. But unfortunately, in 2006, 2007, he had a heart attack and passed away. And I was roped in at this time to work with ANSYS in particular and try to provide that insight to the company. And that was the first time, I think, that a company like Speedo was going into such an advanced form of design. They are a textile company historically, and so for them they were suddenly bringing what they viewed as aerospace sort of technology to support the activity. So we scanned hundreds of swimmers in order to understand basically their positions through the water. We worked with the University of Otago in New Zealand because they had a flume with a transparent wall in which we could stick basically the odd Guinea pig and film them through the water. We could also measure the forces on their body. We work with the University of Champaign in Illinois, I think it's called. And we did some measurements with NASA in order to characterize some of the fabric. That made the big headline because, of course, NASA is recognized as a big thing, and they stole a little bit of the show in that activity. So that was a big collaborative effort, and I think that we got it right because we got over 90% of all the gold medals. God knows how many world records were broken. We followed the rules. The rules were changed afterwards because basically we were doing too well, but we read the rule book. and we just went at it, full steam ahead with the support of the company. It was really, really interesting. In a way, it's a pity that we haven't continued in some ways, because there were quite a few good ideas behind this. So what did we do? A bit of fluid mechanics for you. So here we have a few engineers in the room. What is this plot likely to be based on the color?
Smell.
Sorry?
Smell.
Smell, no. Come on. I've had to endure this for years as Adam sits, or used to sit on the other side of my corridor. I didn't mean the smell, the sarcasm. That and the Liverpudlian accent, because I've got none, of course. So what is it? It's quite obvious, no? You're being shy. This is typical of students. Pressure. Brilliant. Well done. It is pressure. As you can see a buildup of pressure in front of the fingers, in front of the head, and you can see a region of low pressure. Probably the flow is separating, detaching. And basically, what you're experiencing when you're going through any sort of fluid, well, it's not simply the force head-on, it's what happened in your wake. And so with this, we were able to look at how the flow separated, where it separated, use the fabric to pull somebody's bum a little bit more in, maybe, position the hips differently. And we worked with a number of, it was really fascinating, I mean that, working with coaches and physiologists in order to understand how you actually need to position your body at the surface of the water. And you need to sit very high on the water, because of course in the water you have a lot of drag. So it's trying to give that bonus to the swimmer so that basically they can perform really, really well. So we did these sort of studies. As you can see on this picture, there are, and again this was with ANSYS, there are two types of fabrics. The sort of darker fabric is a structural one, because this fabric here was absolutely fantastic. It's like a Teflon, very, very low, basically, friction. However, structurally, it's terrible. So the first test Speedo did, put a swimmer in the tank, and basically water got in between the seams, and the guy ended up with a balloon behind them, a bit like a water parachute. So we had to basically introduce a structural fabric to tighten your end. And as you might have heard, some swimmers used to use two suits. It was declared illegal afterwards, in order to really put themselves in. On a number of occasions, the zip went. They needed assistance to get in those suits, really, really high performance sort of suits. But of course, in order to understand where to place this fabric, we also look at the distribution of shear stress. So when you're going through water, the liquid is basically sliding in layers above your body, and that creates a resistance. And if you look at the distribution between pressure and shear for a swimmer, it's about 70, 30, 80, 20. The dominant factor is, of course, the pressure force, but you've got still 30 to 20% that is due to shear. And that resulted in the suit. I spent a lovely day with Rebecca Adlington, because in 2009 she was awarded, of course, an honorary degree here, and I was a knight in shiny armor. I basically chaperoned for the day. She's a lovely person. It was really a great opportunity. And from time to time, I can't get into it, and it doesn't make me any faster. We do display this suit. We might have used it here, it looks like summer, for one of the open days for the aerospace engineering course, which the IAT was supporting. Gave countless number of lectures and talks, got full FT page, Daily Telegraph page for this adventure. Was really, really interesting from the process of learning, as well how to popularize some of the science. And I'm sure ANSYS got great exposure as well. And I think that the brand, in terms of brand recognition, when Speedo ended the 2008 campaign, they were in the top 6 in terms of sport brand recognition. So it wasn't simply in terms of doing the suits. And by the way, there was no intellectual doping, because all of these suits were given free of charge to whoever wanted them. Nobody can necessarily, well, few people can afford to have a bicycle track in the backyard. These were essentially given. So Speedo got a lot of stick, and I think it was slightly unfair. They got some stick for actually doing well and looking at the rule book and just applying basically good engineering science. So The Right Stuff is the name of a famous movie from which the Sam Shepard picture was extracted before I spent hours watching this. If you've never watched it and you like airplanes, you must watch it. It's an absolute must-have. And of course, the right stuff is also the terminology that was given to the astronauts and test pilots by opposition to the engineers in the early days of flight testing. So I joined to do that, and I loved it. I mean, if truth be told, I had enough in 2006. I had a job back in industry, and I went to see Chris Rudd, and I said, I want to go and do something else. Chris, I think supported by Henry Power and Seamus Garvey, had wind at the time that I think Cassie Simmons was going back to Rolls-Royce. There was some space in the UTC, and they said, well, maybe you could go to mechanical and join the UTC. And they put that to me. I said, yeah, I'd love that. And I've never looked back, and I've never looked at leaving basically the group so far. I spent 10 years in it, and absolutely loved every minute of it. So I was opportunistic and lucky. Otherwise, I would probably have gone back to a consultancy company. So a little bit of aero engines now to educate all of you in those beautiful machines. The line at the bottom is extracted from a Rolls-Royce 2002 manual, so please don't be offended. That's just how it's described. So we, by the way, this is the front of the engine. Oh, if I can find the, yeah, this is the front of the engine. This bit here is what we call the nacelle. That's the bit that you usually see the engine from. The air comes here. This is the big fan at the front that rotates. This bit here is the turbo machinery, the compressors, the turbine at the rear, and if you want to know a bit more, I've put some marker there. And what happens is that, in French for the educated audience, we basically suck the air in. A great part of it in this assembly goes around the engine core, this, okay, it's bypassed. Some of it goes into the compressors at the front. And after this, we compress the air. Now, the Trent engine, typical Trent engine has a operating pressure ratio of 50, so it means that the static pressure between the front of the fan and the rear of the compressor is a ratio of 50. Yeah? Colin Ford, who is one of our visiting professors, told me that the holy grail when he was in the company was 40. Well, the Trent is a 52 ratio at the moment, and I think that the aspiration is to go even higher towards OPRs of maybe 80, I think, in the future. What happens next? Well, you know, we like to make experiments in engineering, so we inject some fuel here, Jet A fuel. We ignite it, and basically through this expansion, we then blow it at the rear, and it goes out. Now here, you have a turbine, because an air engine is driven from the back. So you basically blow the fuel, expand, that drives the turbine, and that drives the entire turbo machinery that is at the front. And of course, a little bit of it goes hot, and it is basically buffered by this cooler white air that has simply been pushed by the fan at the front. Okay? So this is for what we call basically this sort of arrangement where there is a bypass around the engine. Of course, things get hot here because you compress the air. So Adam brought his pump to do a demonstration. If you've all pumped something, and you can test with Adam after the drinks. Thank you, Adam. You have all experienced basically the pump getting hot, so that happens too. And of course here, the entry temperature for the turbine is something like 1700 Kelvin, so it's quite hot. If we didn't manage that carefully, the metal would not survive it. So I'm with a lot of British friends in the room. Have you read this? What's the theatre? What is the play? Macbeth. Yeah, it's a very famous extract from Macbeth. I thought it was perfectly appropriate. Yeah? If we didn't basically do an appropriate liquid cooling, which is what I do for a living when I work with Rolls-Royce, we would get really in serious trouble. And if we let that liquid stagnate, if we didn't remove it from the core of the engine, you know, in these areas around the core here, we would be in serious trouble. So what I do is help basically maintain the temperature in the transmission, in the engine core, using basically liquid to act as a coolant. And we typically inject twice as much oil as we need for basically lubrication, because this other half of the liquid is actually directly utilized for cooling. If you have a 100 megawatt machine, even if you have an efficiency of 99.7%, you take the 0.3%, you apply it, it's still a lot of kilowatts. So you need to manage it. Yes, you really need to manage it. We are present everywhere, so all the blue circles are bits in which I think we work. This is a simplified engine in the transmissions UTC, so we work for all of these bearings that you find pretty much everywhere. That's basically a simplified two-shaft engines. Rolls-Royce work on typically more elaborate arrangements. But we also work on the power offtakes in the accessory region. So the remit of our activity covers a breadth, a range of activity. So it's also very exciting. We work with basically different aspects. Right. So the arrangement I've showed you so far is what we call the turbofan arrangement. Okay. In a turbofan, basically, yes, part of the air, as I said before, goes around the core, around the turbo machinery. Okay? If you take basically the figures for a typical Trent, the bypass per area is 9.3. So we've got basically a ratio of 9 between what goes through the core compared to what goes on the outside. Pressure ratio 52. Every 5 seconds, we swallow, digest, and push the weight of the engine in air. Every 5 seconds, we have the weight of the engine, or the mass, I should say, in air that goes through the engine. It's really impressive stuff. 1.4 ton per second of air will actually go through the engine. Very, very significant numbers. And this arrangement provides basically a large engine, but also a more gentle thrust, if you like. It's also nice on noise levels, and if you take the reference data, which go back to the 1950s and the Comet, we currently deliver engines which are 75% quieter. And if you look at basically the efficiency in fuel per passenger, we are looking at a reduction of 70%. So it's quite significant improvement that have been done with this particular arrangement. The turbofan arrangement is very good in terms of noise management, but also in terms of basically fuel consumptions. And if you manage your fuel consumptions, of course you have less emissions, less NOx or less CO2 that you discharge in the atmosphere, and therefore you are doing your bit for the environment. Okay? That's very, very important. The industry is signed up to the ACARE 2020 guidelines, which show basically a doubling up of the trend of improvement based on historical data by 2020. And of course, the industry is already signed up to Flight Past 2050 with even more drastic figures. One of the challenges we're facing is that we are currently plateauing with some of these. So as we will see later, we need to start introducing some more innovative or radical arrangements. Let's try it next. So this is the arrangement we talked about. Oops, here. So some of the air goes around the core, some goes through the core, is compressed, ignited, and pushed to the turbine. And some of the future arrangements, which we are working on with ATI funding through the Mammoth program with Rolls-Royce, looks at introducing a gearbox at the front. Why is that? Well, very good reason for this. We are making engines which are basically getting larger and larger by diameter, and that's because basically this arrangement is really that of the turbofan, and it delivers far greater efficiencies. Of course, if you take a typical Trent, the diameter is, 118 inches? I think we've got enough Rolls-Royce people in the room that they might agree or disagree. It's 2.99 basically meter in diameter at the front, so you go like this and you fit in. But the challenges with that is that if you link your fan at the front, so the big sort of propeller at the front, to the rest of the turbo machinery, if you want to optimize the performance of the turbo machinery, it needs to run faster. If it runs faster and you have a very large fan, the tip end speed is getting transonic, supersonic. And you therefore damage, basically, the performance of this air that is bypassed around the core, and you lose performance. So what we need to do, whilst embracing the turbofan arrangement, is decouple the fan that pushes the air, right? It's a big propeller, from the turbo machinery, and that requires that system here. Now, this is not Formula One. You know, they have it easy. This is a 100,000 horsepower bit of machinery. So each blade at the fan is basically the performance of a souped-up Formula One engine of the old days. And therefore, developing a gearbox like this is quite a challenge. It's been done before, but this thing flies, so weight is an issue. We can do something like this that is several ton large, but you know, the engine is, what, 6-7 ton for a Trent XWB, something like this per engine. 7.2 basically strikes a chord. And therefore, doing this as light as possible is really, really important. And this is one of the challenges we're working on in the UTC at present. So, yeah, it's difficult basically to say what's impossible, but you can read the rest. Goddard is one of the founding father in the US of rocketry, and his name is borne by one of the NASA Research Center. So one of the things we did in the UTC is look at these drums, the core of the engine. So the engine is facing you now. And of course, the engine is mounted, the shaft is mounted on bearings. We lubricate those balls, but we also basically on the outside here have either the turbo machinery, which compresses the air, and as Adam will no doubt demonstrate to you around drinks, you know, gets warmer as you pump, or you ignite a jet A fuel, which makes the outside quite warm. So injecting oil on these walls is quite desirable to keep them cool. So that's where the modeling comes in. So we have two types of modeling. We have this sort of modeling here. So in there, we chop the space around us into a collection of small boxes. Yeah? And we, of course, know what the governing equations for the liquid flows are. And basically, after this, it's all accountancy. Because you get into one of the boxes, you look at your neighbors. If the fluid is incompressible, yeah? If one of the neighbors wants to come in, well, some of the liquid in that box has to come out. So basically, we do this explicitly here, where we model everything. Problem, of course, is that some of these films are 100 microns thick. So if you want to resolve them, it's very, very tricky. They tend to be below the size of these boxes. So you cannot explicitly resolve them. So what we do is that we discretize the surface. And we represent this through a surface model. So we don't resolve the fluid explicitly in the domain. We only represent it implicitly on the surface. And that's what we spent quite a lot of time working on with the like of Stephen Hibbert. I think Cassie worked on this, Mark Farrell in the old days, Andrew Cliff, sadly departed, in mathematical science, worked on that. And with all good things, and because I'm a good engineer, I like to think, we started with a plan. So we formulated that plan in 2009. This is a Rolls-Royce report, so the Rolls-Royce guys can go and find it. It's basically in the depository. And then we mapped out a program. And all of these are basically EU, ATI, EU project, Innovate UK project. And starting next year, Itandra tells me, I hope, we should have basically the ARIS program, which is a core partnership with Rolls-Royce, to consolidate the model. Really, really chuffed with that. Really good stuff. And all of the red stuff is everything we did wrong that we needed to correct in the subsequent models. Because, of course, when I wrote this, we would have it sorted tomorrow, and Chris Carey, who is in the room, could probably acknowledge that we were going to do it all in one go. I don't know where you are, Chris, but you probably remember those days where within the year we were going to have it. And we struggled. It was quite a challenge. And, of course, we worked in close collaboration with Chris at the time, and others at ANSYS to actually embed this into the software. So what did we do? Well, we started with the first ellipsis program. Yeah, we did this. Fantastic. It was a mass conservative. It was very unstable. What else is there to say? yeah, a bit of a pig, really. And it only worked for the simplest of flow situations. Then I promised Henry Power that there would be 3 slides of equations. So then we basically looked at the problem, and we said, now we need to add some physics to that. So here you have different terms that we incorporated: surface tension forces, gravity, viscosity, hydrostatic pressure. Ed K and Steve and Henry worked on the more mathematical formulation of that. We also looked at the energy equation. Oh yes, by the way, surface tension is what allows this insect to float. It's basically that unbalance in the atomic forces that you have at the interface that creates basically an inner pool for the liquid inward and enables you to float. But it's very important. I put it this because that, believe it or not, is crux to stability in our models. Of course, in the original ANSYS code, and this is not a dig, it's just the way it was, we also made some simplifying assumptions about how to deal with this velocity profile. And we then started to add stabilizing terms, a more complete description of the problem. And we also dealt with the heat transfer, of course. Then came e-brake. And in e-brake, we still had difficulties with these 4 terms. And we needed to add further terms to take into account what we call the full inertia in those models. And that was basically an addition that we put in then. And the heat transfer kept getting improved as a model. Now I'll come back to those terms because they look beautiful when you write them like that, but they are pretty nasty in truth. Easy to calculate, but pretty nasty to derive. So here we are. The first model that you saw, which I said wasn't very good, enabled us to do that. It's called a smooth situation. Smooth situation is that you imagine the drum, the shaft is spinning, it's creating shear inside basically that drum, and you have some liquid that has been projected on the outer wall. If you don't have too much liquid, you probably have enough shear that you can coat it quite nicely. If basically you have too much liquid, well, it starts to pool at the bottom. Okay? If you look at this little diagram, it shows you that gravity and shear forces are perfectly balanced. The other terms in green worth nothing. So for classic lubrication theory, that's quite easy to deal with. Unfortunately, if you want to go to a pool, which we often have in an aero engine, because you might change the speed of rotation, so basically suddenly some of the oil starts to fall at the bottom, you need to evacuate it, we have to go through what is called a shock. And in that shock situation, you reach a point at which shear and gravity forces are perfectly balanced. And at 4 o'clock on this diagram, you have the standing wave with a massive sort of a peak. It can't exist in an engine, I don't believe it, because this is a mathematical situation. But at this point, bingo, in the middle here, the surface tension term is huge. And this guy stabilizes your solution. If you don't have it, you can't go from a smooth solution to a pool solution. The code crashes. It doesn't work. So basically, through the work of Bruce in particular, we really made fantastic progress in seeing this. And it's been proven, by our experimental colleagues at KIT in basically experimental visualizations. And indeed, when we look at the problem from another point of view, we can compute a volumetric flux called Q, and there is indeed a critical flux that is related to the air shear stress that basically you can compute in advance, and when you go through this point, you transit through a shock. Yeah? If you can't get the shock right, well, the code crashes. So basically, if you're looking for pooling, which often happens in an engine, you need to go through a shock. Well, maybe it's not important in the pool situation per se, but the code can't go through it because you can't capture this. And it is a finicky problem. It's really something really small. So, Saturday morning, when you're all gentlemen putting your laundry in the machine and activating them, you'll probably have a thought for this lecture. Because another way to look at this problem is if you take a drum and you make it spin, it's the same effect. Yeah? In an air engine, the drum is static. We drive through shear. In a washing machine, you just drive, well, okay, we don't have baffles. You have baffles in your washing machine, I'm pretty sure. But it's the same effect. Now, I told you about these nasty terms, the additional terms. Here they are. And this is what they look like in derivation. Not difficult to solve, but the derivation of those was basically a little bit tricky. And if we look at this solution, what we see here, this is Ed Kay's mathematical solution. So he was a student of Henry and Stephen Hibbert. Give us the black line here. It has full inertia term because Henry would not do things in half, so it's really beautifully described. Probably challenging to apply to a real geometry. Our model has the advantage that it is nearly as complete, but it can do a full geometry. But at least we used their lessons. And if we look at our half inertia term, we have the red line. So basically, inside a CFD code, we can now do a very mathematically accurate sort of solution. And by the way, if we go back to ellipsis, you can't. The solution just starts to oscillate. Okay? So, as I said, I bet you will never look at your washing machine in the same way again. I defy that. Okay, so what next? The other thing we did, which was very important, we want to know what's going to cost to run those things, is that we went back to theory. This is an equation we got from Lamb. And we then were able to look at what is the discretization, the mesh size that we must have if we are to capture this phenomenology. So in advance, for a given flow problem, we can estimate what is the grid size we must have. And this is basically coming through this term here. And as you can see, we can now quite comfortably predict when the film is going to break up, when it's going to work. Of course, for an ideal geometry, but in advance, we can get a feel for how big the numerical problem is going to be and what it's going to cost. So really, really interesting. Well, next, of course, because we've never done, at the bottom, we have a pool of liquid, so it's quite thick. A sump in a Rolls-Royce engine is probably 10 millimeter, 20 millimeter, 6 deep. But the film can be 50 to 100 microns. So, of course, we wanted to couple the explicit solution to the surface implicit ones, so that we have horses for courses. When the film is thin, we switch to the thin film, which I've showed you before, solution. When it thickens, we have very complex recirculatory flows, we can resolve them. So we did this in Silhouette 2, and you'll like that. So here in brown is the oil that we resolve explicitly. There is a little key here. Okay? And we see it starting to accumulate in a simplified drum. And when you see the colors, we will have switched to plotting the surface, the thin film of the surface. And this is what we can do now, very easily, switching between one model to the other seamlessly. This is for an engine representative condition, max takeoff speeds for those in the know. And here is a thin film forming. And where it accumulates beyond a certain criteria, we switch to basically the explicit resolution, resolve it fully. When it becomes too thin, then we resolve it as a surface solution only. Fantastic stuff, really, really pleasing. Now, what are we doing? Well, because never enough, it is never, never enough. We want now to resolve recirculation in the thin film. So in order to do that, we need to have what we call a higher order discretization, so profiles in the film. So, little diagram here. For my fluid mechanicist colleagues, I know the integrals are not balanced, but I just drew this by hand to explain. So if you have a quadratic profile, typically it would look something like that. If you have something like a cubic or quartic profile, so a polynomial of third or fourth order, you can start to have basically recirculations inside the thin film. And this is really, really interesting. It's a paper we have in review. This is a 2D explicit solution, so we have the grid. This is the experimental measurement. That's our thin film now, inside which we reconstruct the recirculation. So we can now start to look into this. And why do we want to do that? Because for heat transfer in the thin film, the ability to do that is going to be really, really ace, really, really important. So this is work in progress at the moment with Bruce. I would need another 2 hours at least to say what else we do, but of course the oil doesn't arrive miraculously into the bearings. So with Arno and Evgenia, who are somewhere in the room, I think, I can't see them, but somewhere there, we are looking at how we distribute oil. So Evgenia does this with an explicit model, and Arno is working with physics on a meshless, so a method that doesn't need a grid to resolve. And of course, with Cassie and colleagues, we are also doing the experiment. We're also looking at this. So how does the oil behave inside the bearing? The gap here is tens of microns, and we're looking at how we are coating a ball bearing. This is a Rolls-Royce bearing geometry, by the way. It's not a simplified one. And we're looking at how the oil goes, where it goes, and more importantly, how it leaves into the chamber, so that we can have a good boundary condition. That's a piece of work with a PhD student and postdoc of ours called Adeni Akinola, who is now a lecturer at UCLan. And of course, well, the oil doesn't arrive as a beautiful sheet onto the wall. It often arrives as basically ligaments or droplets. And we need to understand how it's going to interact with the surface or with the film. And what you see here is a piece of work done in collaboration with KIT. These are all simulations, because these data did not exist, where we look at how a droplet penetrates a film, how it creates a crown, and how basically the crown develops, how the fingering happens, and how droplets are formed. So each of the droplets that penetrates the film here has 3 million cells into it in order to get the resolution. And we did this, supported by experiments, in order to be able to work out some correlations that we could then return into the full CFD model. Could spend forever talking into this. Right. Yes, I like Goddard, as you will have seen. You can achieve whatever you like, provided you stick at it, is essentially. And we need to give credit when credit is due. Back in the days when I joined, Mark Tittle was in fluid systems. He was working for a colleague of ours called Paul Rees, who might be in the room, who is now a special professor basically in the UTC. And Mark surveyed all basically the Rolls-Royce centers and said, what is it that we need to do to cool the engine and lubricate the engine? And then I worked with Mark, and we translated this into what is it we need to do in order to be able to do that scientifically. And we developed a 6 or 7 year plan. You can't read it, it's deliberate, but that looks like that. And if you look at it, we've just kind of ended it. And the progress we've made is really, really interesting. And when I suggested to Sarah Sharples, I'd like to do my inaugural now, it's because I felt we had come to the end of a cycle just before we start Eris, or we work on Mammoth. And I said, we have a nice story to tell. And that story is fantastic, because I won't tell you the name of the engine, because Rolls-Royce would get rid of me after that, obviously. But that's a real engine geometry, okay? And here is the oil flow in that real engine for the models you've seen before. Yeah? So that's what we can do now. When we started, model would fall apart even for a washing machine. So that's basically what motivated me to say, Sarah, is there any chance that I could run my inaugural? Because I thought there was a really nice cycle and nice story to share with you. And yes, I'm reasonably pleased with what we have achieved as a team in doing that. It's teamwork. Yes, I'm French. Yes, I was mightily peeved off, I think is the right word, with Brexit. That's half of our team who was in the lab on that day. Royal Society basically said, show the UK what basically is the making of your lab. So we are about 47 or 49 in the group now. And that's what we are. So you can see Cassie Simmons, my colleague on experiment, Seamus Garvey, my favorite Irishman just in the corner there, and a number of other people who have been involved here. So the previous case that you've seen in green is done by Andrea here. Arno is the guy who does the meshless work. Evgenia was doing the scoop work that you've seen, currently, of course. Bruce has done a lot of the work on films from Uganda here. Martin Berthold is a Rolls-Royce engineer who works part-time doing a PhD with us. And I'm not going to name everybody else because basically it would take too long. But Daphne here from Mexico and Anthony works on film and droplets, for example. So some of the stuff you've seen. And that's really, really nice to go in that lab and work with those guys. It's an open plan, and I love it. Really, really brilliant. Great dynamics there to work with the guys. So looking ahead, apparently in an inaugural, you need to say where you come from, what you've done, so that your colleagues say, okay, he's worthy of maybe a chair. And then you need to say, well, what's next? And what's next is what I said to you before. We need to have these ultra-high bypass ratio engines. The thing is, if you look at this picture, that's the original. This is the number one, 747, which is very huffing and puffing American engines. They were really struggling at the time. As you can see, the pylon is very low, and the engine is really tiny. This is the latest 747. The pylon is aligned with the wing, and the thing is nearly scraping, basically, on the apron. The engine size has changed dramatically. One way of continuing to do that is, of course, we can't grow indefinitely here, but we might grow a little bit more and reduce the core, make the core work harder, therefore keep it hotter. We might put a gearbox, as I've alluded to before. And of course, a lot of the focus, I think it is one of the focus at ATI for transmission, propulsion, but also for distributed propulsion, is on working out basically the detail of that core. And if we ever go to a so-called open rotor, diameter here is over 4 meters. Yeah? So very large engine. It poses a lot of other issues in terms of installation, in terms of certification. What happens if you lose a blade, which can happen? You don't have any casing to contain basically the blade. But still, you need to pass the power from the turbo machinery in the center onto the outside, and you need some of these fancy, basically, transmissions in order to do that. That's the day after tomorrow. It's coming. Entry in service for some of those? I'm looking at you, Paul. Do you know? What is the entry of service for the Ultrafan?
The Ultrafan, about 2025.
2025. And we want to have an engine, I think, in testing in the next 4 years, probably, something like that. So the challenge is used. At the moment, we are privileged to be working on the simulation of that, and it doesn't exist yet. So we are using some of the stuff you've seen before to preempt design. I wouldn't say it's a first, but it's a new practice of actually driving not heuristically. We don't have the pedigree anymore, but using through simulation and informing design on the fly with the hope of coming back later, of course, to validate. I can't show you the geometry, but The Economist had a very good article on the 2nd of January. You're going to think I read The Economist a lot. I don't. But in January, I had the time, so I read it. And of course, this being a cartoonist, remember I love cartooning, he got a few things wrong. I can't imagine the pilot just, this thing spins in one way only. But, they had fun. And of course, this is preempted by the fact that Rolls-Royce are, of course, developing the Ultrafan. Huge engine. Rolls-Royce have probably 50% of the market in terms of very large engines. But Pratt are, of course, basically doing quite a lot of good work on what we call the 150-seater, equipping a number of basically new and smaller aircraft. Not without challenges, arguably, but this is a very topical topic. Sorry. Right, I'm heading on for the end. We can't have fire in an engine, so it is fire in the belly. What does motivate me? What do I want to do? Well, I'm really, really chuffed, really pleased by what we've accomplished with Cathy and Seamus in, I think, transforming the UTC over that period. I think we were doing okay, probably a mid-table, maybe lower table, sort of a contender. And I'd like to think, not putting Rolls-Royce on the spot, but we are definitely now playing in the, oh my God, European League. I hope for longer. Really doing very well. So that's something I'm really proud about and passionate. And working with ATI and Rolls-Royce, making the center the host to a national facility. Loughborough, I think I've seen John Carrot in the room, is basically, I can't see you, John, but I know you are here. Oh, yes. Is basically the second place that will have this. The Midlands is actually doing very well, Really a good place to actually do this. And that's because universities working with industry and well, arguably government in that instance, have really teamed up together to make that happen. We see Tundra and colleagues in the IAT, managing, I think, our 4th core partnership in Clean Sky 2, and making the University of Nottingham the premier destination of Clean Sky 2 funding, 36 million euros, something like that? 32, sorry, French inflation. Or maybe the exchange rate, who knows. Basically, it's something that is great. And from my point of view, working with the company on the notion of, right first time, moving towards basically, not all CFD naturally, but whole engine sort of simulation. We're working also to, work with Imperial College and Oxford to form a UTP. And the idea behind this is that, well, the sort of challenges we're facing are bigger, need to happen faster, and also they are intrinsically multidisciplinary. So if we can do this from the beginning, we are in a much better position. I think Seamus was in discussion with a well-known German company, not a competitor to Rolls-Royce, dare I say, to look at using the two-shaft test facility already, because they heard about it when we went to Canada, so you can probably figure out who they are. And so that's really good for us. And it's good for Rolls-Royce, because it enables us to keep a team of 7 engineers, I think we have, in the team, plus our administrators to keep basically us and the show on the road. Very interested in progress we are making in Canada as well, with the ATI once again. Of course, there is the IAT adventure that Andy mentioned, initially with Rachel and Pat. I don't know if Pat is here. But more recently with Victoria. I'm delighted that she managed to come and join us because she defected. I mean, we probably trained her well and she proved attractive to another institution, which is a good thing. And of course, Michael Galea, who is also in the room, who is my deputy, who is really driving very strongly, Michael, a lot of the activity with Seamus on bringing basically gas turbine and electrification. And I think we have Leah Wild, who is also in the room, who is just joined us yesterday or the day before yesterday. I can't see you, Leah, but I know you're somewhere in the room. Yes, you are there. And we are yet to basically to continue to reinforce the team. What we're working on at the moment, working with other universities and probably Cranfield, I would say here, is bringing together the strengths we have in power electronics. We have the largest power electronics group in the world, 120 odd people, really championing more electric aircraft, with what we've achieved in gas turbine transmission. That's something that Michael is championing for us through a concept of green, more electric transport theme, really. Of course, we are also strong advocate of the Midlands Engine for Growth. Delighted to have Paul Harris in the room, who was working with us towards the science and innovation audit. And I think we also have Paul Maropoulos in the room, who is basically the PVC leading the transport initiative for Midlands Innovation. And I think it's a great opportunity for Nottingham, but also for Loughborough. I know we've got Loughborough people in the room, Warwick, Birmingham, Aston, and Leicester, who are the 6 universities making this. And maybe more, we've invited others to actually make the case that these 6 have the highest income per capita of IUK funding. And as I've showed you, we can work with industry. We can, I think, hopefully deliver for industry. So we should be trusted maybe to do more, and we'd like to make that case. Cassie, who is somewhere in the room too. Where are you, Cassie? She's there. Of course, worked with the guys in the IAT and with Steve and Trevor Benson in developing a new engineering course on the back of all the track record we had in research. And this course has launched, and I welcome the students of that cohort who I think, at least for some, are in the room. That's great news to have this. And I know we have the Royal Nuclear Society in the room. We are also looking to become a branch. I think we're nearly there. I hope I'm not preempting things. Scott, and I think you are in the room, but we add, I'm not preempting, am I? And we're nearly there. And those of you who attended the fantastic talk by Mark Thomas in the spring, ex-Rolls-Royce, dare I say it, and who now works for Reaction Engine Limited, will have seen how exciting this is and how supportive these guys are of what we do, so it's good. I like that. And a few pictures to conclude. We had Chris Barkey open our new facility on ETB on the 4th of July. It was great. So Chris is the group director for engineering and technology at Rolls-Royce. As you will see, engineers use their hand a lot. We're trying to look, but it was fantastic because we had a lot of seniors who came to see the facilities that the university had invested for us in. And as you can see, they talked, quite a lot. They stayed long, put some music on just to entertain them, did a barbecue after that just to make sure that they didn't go hungry. But they also talked a lot to our researchers. So it was a fantastic event. And if you can convey to Chris how thankful and grateful we were for him giving his time, that was great. And of course, on the 5th of May, I think, we hosted half of the Rolls-Royce board and a fantastic sort of sessions with them in order to convey what it is a university does for the Rolls-Royce board, and I think it was useful. They were really, I think, asking good questions of us, and they talked to the PhD students, to the researchers. We put them forward. We showed them the lab. Graham and Steve, our engineers, I think, showed them into the lab. I think Graham is just here, showing what things happened in the lab, and it was great. And to make things better, we had our friends from Rolls-Royce Deutschland who came over. We had people from the Busan UTC who came over. We had some people from Virginia Tech who came over. So it was a really good evening that we managed to put together. And of course, here is the IAT, Cassie leading the course. You know, outreach. So this is Shubham, purple shirts are our PhD student at Farnborough. Mark Thomas giving a lecture. This is one of our demonstration parts at the Paris Air Show in 2015 on the Clean Skies 2 stand. We provided them with some of that. And of course, Pat received from Eric Dautria with the lead for, I don't quite remember his exact title, so forgive me, for Clean Sky 2, a plaque commemorating the role played by the university in Clean Sky over the year. And yes, quite a lot happening really. You know, 2 Marie Curie programs, 37 Marie Curie students in the IAT at the moment, awards for impact on electric wheels, quite a few things. So really pleased with what we've managed to build. It was, I think, Andy's idea with Pat initially. I'd like to think that with the team, Itandra, Mark, Victoria, Helen, Leah, I'm sure I've missed somebody, Catherine, we are doing a good job of leading that initiative. And it's really nice to also see colleagues come together behind it. However, this time Henry Ford, you know, we need to keep coming together, because if we do that, then we'll make an even greater difference. And those of you who know me know that I love cartoons and drawings. And so in September, when with Michael, Seamus, and others, we were trying to think, how do we do a beacon? Or do we become a beacon of excellence? We came up with some of those things. And the idea here is to drive basically performance across electrification, or from, you know, or toward electrification from the aerospace drive, but also and training and working with Alistair Cairns, Paul Shaler, Anthony LaRocca on internal combustion engines, but also working with UNCC, so the Chinese campus, on basically the marine economy aspect in order to provide a comprehensive solution, this cross-sector, toward how do we actually develop some of these hybrid solutions and how do we go towards some of these more radical solutions. Right, well, some of them exist. This is an Airbus sort of sketch, if you like, and some of them have already been flying. So this is the EFAN, what it looks like, and this is it in flight. I think it flew for the first time at Farnborough 2 years ago. And I think in 2015, they reenacted the Blériot flight. They left from northern France and crossed basically into the UK. John Price knows that very well, of course, because you worked on this with Jean Botti and others at Airbus. But, you know, we can't rest on our laurels. That's Maxwell. I won't ask you any question on that one. Rest assured. It's the X-57, I think, which is basically the program that NASA are currently developing. You know, can we do such a demonstrator in the UK? Maybe, you know, if we pull together, would there be scope for that? Maybe we should ambition to do that. And on that note, I will leave you there. Thank you very much. This is, of course, one of my favorite aerobatics team. They are not flying red aircraft, I'm afraid to say. But I think they are pretty good. If you want to contact me or come and see me, you can basically contact me through this. I said there were basically some exam questions, so now here are the answers. Usually the students like the answers. So what was this first one in the corner, top left corner? Bell X1, that's good. What is the one that is here? So it's an NF-104A, yes, Starfighter indeed. It's N because it's a NASA version. The movie got it wrong because the back of this aircraft had a rocket engine. And Chuck Yeager nearly died in that flight because he switched, of course, a not so good engine, a J79, off in order to switch the rocket engine off, and the gyroscopic effect on this aircraft just caused it to lose control. And he had to basically eject at 108,000 feet. Yeah, very high altitude. And basically, he survived the crash. When they tried to reenact a faked version in the movie, the stuntman died as a result of the stunt. It was quite a challenging sort of event. So yes, good. So 20%. What's this one? French Air Force, the most beautiful aircraft, in my view, ever made. No, this one. Yeah, which one? No, that's a brown. So it's a 2000, and it's a -5F for the record. Okay. This is flying in the Med. This one is indeed a super étendard modernisé, withdrawn from service and to be replaced by the Rafale as of July. And this is its last flight in the original colors. Now, if the Rolls-Royce guys don't know which aircraft this is, then I hit my hat, really. A400M, and what about the other aircraft flown by the French aerobatics team? Alpha Jets, good. Right, well, on that note, if you've scored, let's say, 20 or 40%, you're more than welcome to having a drink. Thank you very much for entertaining me for the evening. I've thoroughly enjoyed it, and I've enjoyed the preparation even more. Thank you.
So thank you very much, Hervé. I hope that all of you got at least 40%. Otherwise, I'm afraid we will have to show you to the door. So I think Hervé has admitted to being determined and energized today. I hope those are characteristics that we would all recognize. I think he also suggested he might be related to Seamus Garvey through migration of ancient ancestors. I think that's
Spain, he told me.
But we've been taken from sediment deposits to swimming to jet engines. And Hervé has answered one of my own burning questions, which is whether or not he'd ever worn the Speedo swimsuit. And he has said no. But he has also shown us how a fundamental understanding of fluid flow can lead to gold medals and to more efficient and to quieter engines. And with that, I think he wants us all to join him outside for some experiments in fluid mechanics focused on two-phase flow. So, thank you.